A flight from New York to London typically takes about 7 hours, but flying the exact same route in the opposite direction takes 8.5 hours. Despite the engines producing the same amount of power, the return trip is a struggle against an invisible, high-altitude current. Thousands of miles away, the European continent will suddenly experience intense heat waves, where record-breaking temperatures persist for weeks without any obvious local cause. At the same time, the Indian subcontinent remains dry for months until massive, torrential rains arrive in early June with almost perfect precision. These occurrences are the results of a single system, massive ribbons of air flowing 9 to 16 kilometers above the Earth. Known as jet streams, they exist at the tropocause, the narrow boundary between the lower atmosphere and the stratosphere. While weather on the ground feels chaotic, the jet streams act as the primary mechanism directing the movement and intensity of the planet's climate. This global system starts with the sun. Because the Earth is a sphere, solar energy hits the equator directly, creating a concentrated belt of heat. At the poles, that same energy arrives at a slanted angle, spreading out over a much larger area, leaving those regions freezing. This temperature gap turns the atmosphere into a giant engine. As air at the equator absorbs heat, it expands and rises. At the poles, the air is cold and dense, so it sinks toward the surface. Rising equatorial air leaves a low-pressure zone. To balance this, heavy, high-pressure polar air tries to rush toward the equator in a straight line. This pressure gradient, the difference between the heavy polar air and the light equatorial air, is the battery powering all global wind. It sets the stage for a massive atmospheric collision. But the air never travels in a straight line. As the wind rushes toward the equator, the Earth is constantly rotating on its axis. This spin creates an apparent deflection called the Coriolis force. In the northern hemisphere, this force causes moving air to be deflected to the right. In the southern hemisphere, it bends to the left. Instead of crossing the planet, the wind is forced into narrow, high-speed bands flowing west to east. These bands don't stay straight. They develop massive northward and southward curves called Rossby waves. The Coriolis force transforms simple north-south breezes into organized 400 km/h rivers of air that effectively contain the world's weather systems. To see how these physics affect life on the ground, look at the Tibetan Plateau, an immense high-altitude landmass that absorbs massive solar heat during summer. In the winter, a specific current called the subtropical westerly jet sits south of the Himalayas. Moving at high speed, it acts as a barrier, preventing moist ocean air from advancing into the subcontinent, keeping the region dry. As summer approaches, the intense heating of the Tibetan Plateau changes the upper-level pressure. This shift forces the westerly jet to move north of the Himalayas, finally clearing the path over the Indian subcontinent. At the same time, a new current, the tropical easterly jet, develops and flows from east to west. This current strengthens the upward movement of moist air, drawing ocean moisture into India to create torrential monsoon rains. The timing of this seasonal movement is everything. The survival of India's agricultural economy depends entirely on the precise coordination of these two high-altitude currents. We interact with these currents daily. Airlines specifically map their routes to catch these tailwinds, which can save thousands of liters of fuel and cut over an hour off a long-haul flight. However, the edges of these jets are often turbulent. Pilots must carefully navigate these boundaries to avoid clear air turbulence, sudden, violent shaking that occurs in perfectly clear skies where weather radar sees nothing. On the ground, the shape of the Rossby waves determines our seasonal extremes. When a wave dips far to the south, it pulls freezing Arctic air into regions that are normally warm, causing sudden cold spells and heavy snow. Conversely, when a wave bulges toward the north, it draws tropical heat into high latitudes, resulting in those record-breaking European heat waves. Whether you are flying at 30,000 feet or experiencing an unseasonable freeze, the conditions on the ground are being directed by the position and speed of the jet stream. Today, this atmospheric engine is beginning to change. Global temperatures are rising, but the Arctic is warming much faster than the equator, causing polar ice to melt. Because jet streams are driven by the temperature difference between the poles and the equator, A warmer Arctic shrinks that gap. This weakens the pressure gradient, causing the jet stream to slow down and its waves to become deeper and more exaggerated. A slower jet stream is more likely to get stuck. Instead of weather systems moving across the continent, they stall. This causes heat waves to turn into prolonged droughts and normal rain into persistent flooding storms. Next time you look up at the sky, remember that those roaring rivers of air just beyond the clouds are the forces determining whether the weather in your own backyard stays calm or turns into an extreme.